Okay, so we have a theorem. Nine point 2.2, and that says for any integer n with n greater than or equal to 1, the number permutations of a set with n elements is n factorial, which would equal 1 times 2 times 3 times 4, dot, 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 all the way up until n. And factorials are going to be used a lot in probability. Actually, we've already seen these. I mean, I showed them to y'all a little bit earlier in the semester when we were talking about binomial expansion. And yes, binomial expansion is going to have a lot of applications of probability. We're going to see that here in just a second. So let's say we had a set with 3 elements. Okay. So okay. So we've got this set of 3 elements, and we want to consider all possible permutations of this set. Okay. So we'd start off, let's put A at the beginning, and then said, okay, well, A, B, C. Well, A, C, B would be another permutation of that. Okay. And why don't we put B at the beginning? So B, A, C, B, C, A, C, B, A, CAB. And so what do we end up with? These possible combinations would be, we get 1, 2, 3, 4, 5, and 6. So 3 factorial, which would equal 1 times 2 times 3, equals 6. But if you went to larger sets, you wouldn't want to write down all of these formulas. So if we had, let's say, the set A, B, C, D, well, you could start out, A, B, C, D, A, B, D, C, da, da, da. It's going to take a long time to figure that out. So, but there are 4 elements in the set. So 4 factorial, which would equal 1 times 2 times 3 times 4, that would be 6 times 4, which equals 24. So there are 24 possible permutations of this set. Okay? And if we want to step further, I mean, you really don't want to try to write all of these out. But think about this. A, B, C, D, E. Wow. If you wanted to, A, A, B, C, D, E, and then we can swap the last two terms, C, E, D, like that, go down forever. Well, the number of possible permutations of this would be 5 factorial, which equals 1 times 2 times 3 times 4 times 5. Okay, and so 1 times 2 times 3 times 4 times 5, that's 6 times 4. 6 times 4 is 24, and then 24 times 5 would be 120. So that would be 120 possible combinations that can be incorporated into that. That's how many permutations you get. So you can see factorials, we jumped from 24 to 120. Factorials, the number of possible combinations that can exist within this, they explode. They get very big, very fast. And so in some cases you would say that's a bad thing because you end up with so many different combinations. But in other ways, factorials are used where you actually divide by them. And in that case, they're actually very good. Mainly I'm speaking of Taylor series, but we'll talk a little bit more about that later on. Okay. So now, let's say we had a different type of permutation. So this is just saying, within this entire set, A, B, C, D, and E, if I'm going to use all of the elements within that set to create a permutation, this is the number of possible outcomes from using all of the numbers within that set, okay? But what if we decide instead we're not going to use all of the numbers within that set or all of the elements within that set? So with a deck of cards, the number of permutations of a deck of cards would be 52 factorial. Think about how big 52 factorial would actually be. That is a huge number of combinations that you can create with a deck of cards. Think about every single way that you could shuffle a deck and get a different combination. That 52, what is 52 factorial? 1 times 2 times 3 times 4 times 5 times 6, all the way up to 52. That's a huge number of possible permutations within that set. But what do we do when we play cards? We don't choose all 52 numbers. I mean, think about this. If you were going to take a deck of cards and randomly say, I am going to have all the cards completely in sequential order, going hearts, diamonds, clubs, spades. And what is the probability out of all of those possible combinations that you would get that one? That is extremely unlikely, okay? That would be what, from the previous video, we said that would be 1 divided by 52 factorial. 1 divided by 52 factorial is an insanely small number, okay? But when we play cards, we don't choose a single deck, okay? What do? You get 5 cards, okay? And then we can talk later about, well, what if you hand some cards back over and get some cards back. So we have, instead of these permutations, which is consuming all elements of that set, let's say we had a different type of permutation, okay? So this is referred to as an arc permutation. Of a set of n elements is an ordered selection of R elements taken from the set in crap, I ran out of room. That's in elements. Bear by a second to write that down. So an R permutation of a set of n elements is an ordered selection of R elements taken from the set of n elements. Okay, now this seems like a kind of, it's a long statement that might seem a little confusing, but what is meant by this, well, all right, as an example of cards in a deck, what would n be? It would be 52 elements. There's 52 cards in the deck, okay? A dealer is going to deal you 5 cards. What is what is R? R is 5, okay? So and this one is a little bit different because this is in a general sense, okay? So if you ended up with, all right, so it says all possible combinations of 5 that could exist within the set of 52 cards, okay? And this is another thing to notice is that this is an ordered selection, okay? So if I got, right, so normally when you have cards, when you get your 5 cards, you mix them around, right? I normally put the high cards on one end, the low cards on the other end, just to see what possible combinations I could get. Now this is an ordered set, meaning that the order actually matters. So, 2 things that would be different if you had, say, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay, 2, 3, 4, 6, 5 would be a different element. Okay, so this is, since it's an ordered set, because 2, 3, 4, 5, 6, and 2, 3, 4, 6, 5 are different things. This is not exactly the number of combination of hands that you can get within a deck of cards. Okay. Well, let's look at our formulas for this. The number of possible permutations, P of n r would equal n times n minus 1 times n minus 2 all the way off to n minus r plus 1. Okay. Y'all will probably see this formula more often. Okay. Now, how are these things equivalent when talking about factorials? One of the things about factorials is there's with a lot of these formulas, there's a lot of cancellation that ends up going on, okay? So why P of n r equaling this thing up here actually being equal to this thing right here? Well, let's have a look. Let's say we did let's say okay, 5 minus 3 is 2. Okay. Well, the 2 and the 1 would cancel each other out. Okay, so 5 times 4 times 3. And so when I look at this one, what would this become, this last term right here? Be 5 minus 3, which would be 2, and then 2 plus 1 is 3. And so that's how I ended up with that 3 on the end right there, just from the cancellations. Okay. So let's look at this in just a basic set. It's a little bit trickier to do with a full hand of cards because you can't write out all the examples. Okay. Let's say we had A, B, C, and D. Okay. Okay. And let's say, and we're going to look for all second order permutations of the set. Well, before you just start looking for all of the second order permutations of this set, why don't we say, okay, I want to figure out how many there would actually be, because I've got to get to that number. So, P of 4, 2 would equal 4 factorial divided by 4 minus 2 factorial, which would equal 4 factorial. And then 4 minus 2 would be 2 factorial. And so that's 4 times 3 times 2 times 1 divided by 2 times 1. And then, well, 2 times 1 and 2 times 1 cancel each other out. Okay, so there are 12 possible, okay, move that up. 12 possible second order permutations of just this set A, B, C, D. Okay. So let's figure out, let's just have a look at this and see if we can't figure this out. Okay, so I've got my elements A, B, C, and D. Okay, so I'm going to try to write down all 12 second order permutations of the set A, B, C, D. Now, what could these possibly be? I know I have to get to 12. Okay, so that's the number that I'm going for. Okay. Well, let's just start. A and B could be together. Okay, that's one permutations. A could match with C, A could match with D, B could match with A, B could match with C, B could match with D, C could match with A, C could match with B, C could match with D, D could match with A, D could match with B, and D could match with C. And so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Now, the thing to pay attention about this is that this is talking about ordered permutations. Order matters. Okay? This isn't like a hand of cards where you can start switching the face cards to one end, the low cards to the other end, and then decide you're going to swap some out. So, AB and BA
are two different things because this is ordered, okay? So this is not the exact same thing as saying I'm going to just choose 5 cards from a deck of cards and that's the set I have. That would be a non-ordered set because I can move my cards around. I can mess around with my hand and try to put it into different orders to try to see, well, maybe some of the low cards I want to throw away and then hopefully I'll get something back from the dealer on the next set. So when talking about ordered permutations, order matters. Okay. Okay, so let's say we want to consider a problem where order doesn't matter. Okay, so instead of talking about ordered permutations in this case, instead what are we going to refer to it as is actually subsets where order does not matter. Okay, so if we start talking about it in terms of that, okay, so on this problem we have an Rth permutation of a set of n elements, which is an ordered selection of R elements taken from the set of n. Okay, great. All right. The number of subsets Okay. Now, the number of subsets of size R that can be chosen from a set of size n, this is often referred to as n choose R. Okay. And so, in a problem like this, you're talking, all right, subsets. Subsets. Sets. Don't watch too much stuff about cults. The number of subsets of size R that can be chosen from a set of size n. So this is, when you're talking about subsets instead of ordered pairs, this means that when you're given 5 cards, the order of those 5 cards doesn't matter. So if I want to put the face cards at one end and the numbered cards at the other end to try to figure out what kind of hand I was dealing with, that's totally fine. You can rearrange the 5 cards that you're given. So if you have 2, 3, 4, 5, 6, that's the exact same thing as 2, 3, 4, 6, 5. Okay? So that's the difference between a subset and an actual ordered pair. This does not require order. Okay? So in choose R, this is n factorial divided by R factorial So this looks very similar to the formula that we were looking at just a second ago. And if you look at the difference between these, what is the difference between these two formulas? very similar, but the probability of ordered sets does not contain this extra factorial, the r factorial bottom. So, and what's going to happen when you divide by this extra r factorial? You are going to end up with fewer possibilities. Why? Because since order does not matter in this case, you're going to end up with fewer possibilities because 2, 3, 4, 5, 6 is the same thing as 2, 3, 4, 6, 5, or any ordering of those numbers. Okay. So let's have a look at the problem that we just did a second ago. So, okay, when I did the possibility of all permutations, I mean second order permutations of this set right here. Let's have a all right, and we're going to say four choose two. All right, so what would that become? Four times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. So 4 times 3 times 2 times 1. Well, 2 times 1 times 2 times 1 is 4, so 4, that would come out to just being 3 times 2, which equals 6. All right. Okay, so to basically get this set, what we need to do is we need to go through and disregard anything that gets repeated. Okay? So how are we going to do this? Let's look at our previous set. I'll write it down again. Okay, so all second ordered permutations of this set of 4 was a B, a C, a D, B A, B C, B D, and then I want to say C A, C B, C D, D A, D B, D C. Okay. Now because of AB, BA is out. Okay? And then because of AC, CA is out of the set. Okay? And then because of AD, DA is out of the set. Okay? Does anybody see the next one that cancels? Okay? Because of BC, CB is out. They're the same thing. Okay? And then when I go down to this one right here, BD, well, what is that going to eliminate?
eliminate that one, because those are the same ones. And CD with DC, knock itself out. And so what do we end up with? Possible subsets of this would be 1, 2, 3, 4, 5, and 6. Okay. So that's the main difference between these equations, is one is about ordered sets and one is about not ordered sets. All right, let me phrase this in a slightly different way. One is about ordered permutations, and the other one is about subsets of unordered permutations of a certain size. Okay? So let's look at a deck of cards. So a deck of cards would be, if we're playing poker, okay? So let's say, how many possible hands can you get in poker? Okay. So the number of possible hands in poker is going to be, we have a deck of 52 cards, okay? You can pick out, the dealer can deal you 5 cards, okay? We're not gonna go into swapping out cards just yet. So if I've got a deck of 52 cards and I choose 5 cards from that deck, okay? So if, I'm saying, all right, 52 cards, choose 5. So 52 choose 5 would equal now 52 factorial divided by 5 factorial times 52 minus 5 factorial. Alright, 52 minus 5 would be 47, so that would become 52 factorial divided by 5 factorial, and then multiplied by 52 minus 5 is 47 factorial. Do some cancellation inside of here, and so that would become 52 times 51 times 50 times 49 times 48 divided by 5 times 4 times 3 times 2 times 1. And what does this come out to? $2,598,960 possible hands. That's a long enough